Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. We're a little late today, but that's all right. Basically, I had to get this stuff building again, and it was a lot harder than I remembered, just because a lot of things have changed in this technology. Anyway, this is my last stream that I plan on doing before revision, so I really didn't want to miss it. So even though we're an hour late, it's going to be okay, I think. Anyway, what we're going to go over today is new. So we've been going over a lot of the tooling and a lot of demos that I've worked on previously in sort of preparation for making this demo scene stream where we actually use the tools to make stuff. I think that'll be pretty fun. But the last demo I wanted to go over was called New, and this is actually the first Super Nintendo that I put out, or Super Nintendo demo that I put out. This won the demo compo at the Gathering 2014. Was the first time our tracker was ever used in, well, like a Rio project, other than some awesome tracks that Citrix made that he played out, at least, I think. But yeah, first time it was ever used in anything released. It's also sort of the beginning of the Mammon Machine project, which I went over a couple weeks ago, which we are sort of currently using to do SNES demos. I mean, currently is a little relative. But yeah, our current tech is basically what that is. So this basically covers a lot of the same things like a custom assembler, different ways of handling graphics from .NET. This is before we moved everything to F#. This was all .NET stuff with C#. Has a little video compressor in it. The runtime code is pretty much the same as a lot of other things, or as a lot of... I'm sorry, I'm pretty scatterbrained getting all this stuff set up. Anyway, let's do this. Let's just go ahead and watch this demo first. And I think that'll start us off on the right foot. I had to re-export really quickly, though, because I just realized that a couple of my repos were out of sync and the music didn't sound right. So hopefully this works. All right. So this is new. Cool. So yeah, so we put this out in 2014. Basically did it in a mad rush up to the Gathering in like about 2 weeks it took to do basically everything, including the soundtrack, including the tech behind it. It was extremely fun. This was easily one of the most fun projects I've ever worked on. And it's kind of weird how it all fits together. So I want to kind of go over some of the tech behind this, particularly the OpenGL demo that actually makes all the visuals initially, and some of the video compression tech, because I think that'll be pretty cool. The rest is fairly straightforward. Oh, and also I want to go over some of the like artistic inspirations, kind of where ideas for certain bits came from. By the way, hey guys in the chat, Zalex does. How's it going? Void00, Spaculo, Phil Daddy 69, Studio C, Soding, TJ. space effect. Good to see you guys. Whew. All right. So basically, what this is sort of technically speaking, this is an OpenGL demo that gets video compressed. And then that video is played back on the Super Nintendo, along with all the audio stuff, of course, which, you know, we use our custom tracker for. But basically, the OpenGL demo, I can run this here. It has a tiny little viewport. This is written This is written in C# against OpenTK. So it's basically pretty straightforward OpenGL code. And then I'm using Rocket down here to do the sync stuff. Now this is the official Rocket editor. In fact, this is the official one from a couple years ago. So it looks a lot different than the one that we currently use. But basically, if I play this, I can sort of move around in time and basically play the demo, and you can see kind of how things are synced. Basically, everything's written with immediate mode GL out of pure laziness, because that was the quickest thing possible that I could set up, is just set up a C# thing and then pull this together. Basically, I think I started the visuals in the last week, and the rest of the time was spent, well, we spent a lot of time kind of talking about different effects and building kind of effects kind of the classic way, and then a couple weeks to the party, we were running out of time, and it was like crunch time at work, and I didn't have enough time to do, you know, proper tech, so I just kind of thought about what could I do, what crazy things could I do. And I started doing some math in my head, and I was thinking about the DMA on the SNES. And particularly, I think I did the math, and in one VBlank, if all you did was DMA, you can get like 3 kilobytes of data over that. Now, that's actually pretty good. If you look at a 4-color image, I think I just did some like basic math at the time and realized that it's this around, like a full color image was something like 2.5K or something. I can't remember the math exactly, and where that came from, but I would just kind of thought, you know, this could actually work. So what I did is I threw together a little test, just had a couple triangles spinning around, and it would fade in and fade out. And I even wrote this little scripting thing for this, just to see how big that was and what that actually looked like. It worked really well, and of course the video played really smoothly, but at 50 FPS, the video that it was able to play lasted about 4 seconds, and then we ran out of ROM space. Actually, let me calculate how long that actually was. I remember it, I don't think it was actually 4 seconds, but it was really, really short. So, for example, it was 50 frames a second by 3 kilobytes per frame. And then, yeah, so that we can say that this is about 150,000. So if we take our 4 meg limit, that lasts about 26 seconds. That's not long enough for a demo. And plus we had the music, which doesn't take up that much space. It's only 64K, but yeah. So this was assuming every frame was 3K. I think they were actually a little bit larger. But yeah, there's some back of the napkin math to figure that out. Anyway, so of course that doesn't work out. But with that test, I figured, okay, if I could make a clever little compressor that would just update the things via DMA that would actually change, this could actually be viable. At the same time, I had already been thinking about these tools to kind of, I talked about this in the previous streams I did about the man machine and our current Super Nintendo tech. Basically coming up with these systems to manage the data that's in VRAM and kind of do that automatically, and then just write the CPU code for the effects that you're interested in. And so I was kind of already thinking in that headspace and thinking about the sort of bytecode that I would use to actually interpret this kind of stuff. But this was the first time that it all, like, we were kind of forced with the deadline to actually make something real. And I say we, but really at this point it was basically just me. I did the music, I did basically all the tech, did the little OpenGL demo. And again, it was extremely fun, but it was very, very, very busy and a lot of work. Anyway, it was pretty cool. So I want to kind of go over some of these effects. By the way, even the design was kind of outsourced, like on that sort of strict time limit. By the way, guys, if you haven't heard of Beeple, Beeple makes awesome stuff. This is linked to a video that he put out called 4-Color Process, where he was just making some scenes out of 4 colors. And if you watch this, you'll notice a lot of it looks pretty familiar. like that globule thing, this tunnel thing. So this is basically where sort of the design came from, and also the idea to use 4 colors. And the reason why I wanted to use 4 colors again was just to keep the data rate down. Because even though this uses video compression, if you do the math, it starts to be, you start to really push that in terms of bandwidth. Another thing, of course, that I discovered when actually doing this video compressor is that, okay, if you do like 1 DMA run per frame, you can get like 3.5 kilobytes or something. But as soon as you start doing more than 1 DMA run per VBlank, you actually start running out of that time pretty quickly, and you really need to cut down that rate. So basically, the whole video compressor is kind of optimizing for that in particular, is the fact that it is going to be played back on the SNES. I also tried a ton of things with the video compression to do like dithering or those kind of things, and it actually ended up just increasing the data rate when you only have 4 colors. And so going for this look where it was only 4 colors and just very sort of vibrant colors, actually ended up being a huge advantage, because otherwise, like if things were too soft, this would just compress really badly. And I can show you, we can recompress this a couple times on the stream too, and I can show you what happens when you go over the data rate, because even with all of these visuals kind of tailored to this technique, there were still a couple times, particularly with this tunnel scene down here, that particularly when like things would move around the edges, you get a lot of movement here, and then a lot of pixels on the screen have to change, so we have to update a lot of things, especially with the shake. And I actually had to adjust the rates at which like things would rotate and things would move in order for this to even work under like the best conditions possible. The video compressor still had trouble with it. So it was really finicky, but it was pretty fun. So yeah, so the demo itself, or the OpenGL demo, I should say, is pretty simple stuff. We have a few different parts. I think there's only like 3 or 4 different distinct parts here. We have the globule, or sorry, not what's this one called? It's been like 3 years since I looked at this, so I gotta kind of reacquaint myself with this, but this will be all right. Rangs. This one's called Rangs. So what this is it's basically just a few different color rings, and you can basically imagine an arc, like a model of an arc, where we have kind of the color it is, the radius, like inner and outer radius. We have kind of a rotation offset for where the beginning and end are, and we can basically control all of that with sine waves. And then we also have a camera. So basically everything in this little OpenGL demo is 3D, so we move a camera around to display some of these. So for example, this is done on 2D plane, but then we kind of back the camera away, and that's what does that. There's also, you can see there's this, I think it's out here, where it says the tab position. So these tabs are these things, and they just sort of click out from the middle and just look nice. That's all they do. I think there's some more bits over here, but there's the actual, which ones are active here. But basically how this is hooked up is this little demo here is basically written, again, with OpenGL. And then it takes input from this tracker that are just like float values for different things. So for example, we can look at the code for the rangs effect here. We have, I'll pull this up here. So this is going to render 1 frame of this effect. So we have the width and our height. We have some sync thing. Missile, by the way, is my little abstraction layer for .NET over Rocket. I can't remember why I didn't use Rocket.NET, probably because it didn't build at the time. There's a lot of issues with those kind of things. And then, yeah, the current frame time, or the current time in seconds of the demo that we need to render the frame for. So literally, I just clear the screen with some background color, get a new random object, grab these sync values. So like there's the camera distance, the bump. So bump is like, you'll see if I move down here, you'll see like there, it starts to get shaky. That's the bump. And we do that, we sync that with the kick drum. In fact, I should see that over here. This is the bump track. Just kind of hits with the kick. And then it also takes the size of the overall rings and then the different tab position, all that kind of stuff. There's also the fill, because we get different fill for the different tabs, and that's how we kind of get, like, I think the tab position here is how far this is going outwards. And then it just does a little sinus scale on that. And then we have a bunch of different versions of these tabs where we have fills, and then there's different track values for those. But basically, we shake the camera using this camera shake thing. And the whole thing is, this is all fixed function GL. So we have this sort of this worldview matrix that we adjust to do all the transformations, including the camera stuff. And so, for example, all this does is just does GL translate with some random numbers here with an amount. And that just will adjust the model view matrix, and we just, okay, that's how we do the camera, instead of even differentiating between the two matrices. It's just streamlined to be as convenient as possible for just me to write this really quickly. So we're going to shake the camera. We're also going to translate based on the camera distance, so we kind of move away from the scene here. There's 3 rings. Each one of these has some time, has some thickness, inner radius, outer radius, and then I draw a ring here. And the ring is going to be just some quads in a ring shape. So that's pretty simple. This helpers module, by the way, just has a bunch of these, like draw a bar, draw a sphere, shake the camera, some stuff from colors and vectors, because OpenGL has stuff for vectors, and then the Windows stuff has stuff for colors. So I think it was Windows system drawing. I think that's some GDI stuff. Might be more generic than that. I don't remember. Yeah, and then we draw these tabs as well. Draw little bars here. So it's that simple for that effect. But I think it looks nice. And it's, of course, the sync is like what makes this... The sync is what makes this work. Let me turn that down a bit. And then we move on to the next part. So one of the things that I wanted to do with this in particular is, if I'm going to do like a 4-color OpenGL demo, then I want to sort of make that as flowy as possible and kind of milk all we can out of doing that. Like because we have that, we want to use sync a lot, and we want to use we just want to take advantage of that tech as much as possible, and sort of play the strengths of the technique. So we're really heavy on sync, and really heavy with like transitions and just general emotion, just making things look nice. So what happens here is these tabs all go here, and then I sort of scale all of them down into this circle. And I think here we actually change scenes. But the motion makes it all look like it kind of flows into the next part, but I think it just does a hard cut. There. And then we're on the globule scene. And you can see over here on the left we have the part. And that's picking the different things. So the globule part has a few more interesting things. If I kind of show you what this looks like, there's a few different things that happen. First of all, there's a bunch of these small spheres that all sort of move out, and they have these lines between them. And that's literally just drawn. The spheres are drawn with geobegin, geoend, and then some quads. And the lines, I think, just connect adjacent spheres. So I think I have a list of spheres that I'm just updating here, and then the lines between them. And then eventually we have another sphere in the middle that's the same color as the background, that's kind of in the center of the scene. So these spheres, the way they move is we basically, if you can imagine this outer sphere that's growing here, I can wait for that to grow all the way. There we go. Oh, whoops. Clicking all the wrong windows. If you you can kind of see this center sphere as it comes in here. And basically what I do is I take some basically random like sine waves for X, Y, and Z. And with some time offset and some time scaling, you can basically have these spheres kind of move in this like unit square almost, in this sort of smooth way. Now, if you take that position within that unit square and you normalize all the coordinates for the spheres and then multiply them by some radius, you get the same kind of random motion, but they're moving along the surface of a sphere, basically. And sometimes it creates these kind of fun movements where, like one of these, for example, will just go kind of around the sphere really quickly. And that happens when it would have gone near the center of the unit square, but because it's all normalized, you get this kind of swoopy motion. anyway, it's a really simple thing to do, but I really like how that moves. But yeah, so the globules are, yeah, the small spheres are always kind of moving in that motion. But then we also introduce this this other sphere. At the same time, they have these different fade, because these little balls can either be this lighter blue or this green color, or white, and they just kind of fade there. So we're just kind of morphing things and just taking simple stuff and making it transform in some way that I think is cool. When that comes in, we have sort of the final actor in this scene, which is the rings behind it. And these rings are really simple. It's basically we just draw one ring. I think we draw two at a time. I think there's a couple that move back and forth. I think they just are really large, and their radius is based on the sinus. So we basically just draw those, but then on top of those, we draw a bunch of bars that are the same color as the background color, just to break these up. And the bars have an increasing width as it kind of goes down the screen. And I think those also tilt on kind of a sinus pattern. And when it's all together, then we get kind of cool motion. And again, the camera shake with the bump thing. And we also scale the radius of the inner sphere and the distance here. And then eventually that fades out. Now the fade out here is actually really important in terms of the video compression tech, because we basically have to get all the way down to nothing here before we start this effect. I had it so that we were doing both at the same time, and it was kind of a more fluid transition, but there ended up being way too much changing on the screen between frames. And then we get some nasty artifacts. And that is what we wanted to avoid like the plague. So that's kind of fun. Anyway, the code for that is really simple. Basically, the kind of thing you'd expect. How much the rings are faded in, the whole globule fade, which I think, yeah, fades it to white. Pretty simple. I mean, we just have the camera shake here. Okay, yeah, so I actually have it split up from the between the background and the foreground. So the background, we have a little bit of camera shake. And then here, yeah, we have the two rings. So there's basically just with random numbers. They're just going to kind of move on some sinus stuff. Or not even on a sinus. This actually just does modulo. So they just keep growing, and they will repeat after that. Base Effect, have you ever tried to render demo in 8-bit? If you've seen my Game Boy demos, those were done kind of the traditional way. And yeah, a bunch of other old school stuff. I've done a bunch of C64 stuff I haven't released as well. So I've done it that way. It's just fun to do it this way as well. So yeah, so those rings are kind of moving from the center out. And then here we have the different bars, and that just kind of rotates like this again, just kind of skews those. And just draw a bunch of bars here. Then the foreground, we're just going to reset the camera. I probably did these as two separate things just because it was easier than trying to like compose them in 3D and make one scene. It's probably just easier to do the 2D elements and think of them that way. Base Effect, I mean to render that demo. No, I haven't tried. Not much of a point, I think. Because it's, yeah, I don't know. I do want to do some polygon-based stuff. I do want to do some polygon-based stuff on SNES eventually. That is software rendered, but I wouldn't just convert this one for the sake of converting it, because I'm pretty happy with this tech, even though it wasn't traditional stuff. But yeah, so the foreground then shakes the camera. Got depth test. Makes this big sphere. Yeah, and then with the sync track, it can grow. And then we can color the small ball colors. Mix those with white, and then we just draw 8 small different balls. We keep track of the last position in a vector so that we can draw these lines between the current one and the last one. But basically, it just has these random numbers that determine how they move along this sort of unit square. But of course, we seed the random number generator with the same seed every frame. So they're not too shaky. So that's pretty straightforward. And then this is the tunnel scene. And this literally just draws, I think these are also rings, if I remember correctly, because I'm pretty sure that the ring object has a resolution thing here. And if you turn that down to 6, then you should get these sort of hexagon shapes. And this just draws a few of those. Again, there's some sinuses that rotate them. I think there's some random colors as well to determine, which color they are. And then also we draw a ground plane here as well to kind of cut that off. This is one of the ones that, if you look at the original Beeple video, I really wanted to do a lot more with this, but just because it changed so many pixels on the screen in between frames, it just wasn't feasible with this technique. Code for that is crazy simple. We have a bunch of these tunnel pieces, and the tunnel piece has basically a Z position and a color. And I believe that, when I create the effect initially, then I just make a bunch of these tunnel pieces, like 20 of them here. And then to render them, I just loop through all of them and then draw those. So these ones aren't generated every frame there. I create a little data structure at the beginning, and then I draw these. Oh, here I actually draw the whole segments here. That's kind of funny. I bet I made this before making the ring thing then. Because it seems like I'm doing this code again. But this is all very basic trigonometry and just kind of moving points. So this is the kind of stuff I've done since I was like 12. So I just write this stuff really fast. Waste Fellow, how's it going? Thanks for the follow. So that's the tunnel. Very, very simple. I think I have a couple things to like control the radius of all these as well. And I think I use that to fade it out here like that. And then of course there's the camera that's moving sort of forward, and we have more shake here as well. And it gets really shaky because of that kick drum. So this part, I actually, I was like throwing around ideas for logos for Ferris. For me, is like my music artist, but also is doing demos because I did this demo basically solo. And so I was playing around with those kind of logos, and this is the one I was thinking of for a while. I don't like it anymore, but it made it in the demo. But really, it just added that cool little sync point where you have the in the music, and then you just kind of see those little flashing things. And again, that's just 3 bars, so it's not very exciting. But it looks nice. And then we have the pyramid scene, and the pyramid scene is kind of the coolest scene in here, even though, again, it's also very, very simple. But looks really nice. Move away 008 looks like the hamburger menu on Android. Yeah, basically is, just with hard edges rather than soft ones. Waste Fellow, do you like Oslo? I do like Oslo. I think it's kind of an ugly city, but I like the weather. I like how I live downtown enough that I'm close to everything. And I like where I work. So basically this one, what we do is I wrote a function that could basically just draw a segment of a pyramid. Now let me pull that up. Because that's basically the key to all this whole effect here. Okay, so I even put that in helpers. So this is the pyramid section. It takes an outer color, which describes. So let me see if I can get down here. So the outer color describes this color, and then the inner color describes this color. So you can basically imagine it as like a segment of a pyramid. The outer one is the 4 walls, and then the inner color is sort of the guts. That's what I was thinking of when I made it. Then you have X position, Y position, and Z position, so you can offset these in all directions. I think I tried to offset these like X and Z, and I don't like how it looked, so I only ended up offsetting them in Y. We also have scale in all those directions, or actually just scale X, scale Y. Don't know why I didn't have scale Z. Who knows? There's a start and an end. So the start and end, I believe, are normalized, so they go from 0 to 1. And what that is like 0 would be the base of the pyramid, and 1 would be the tip here. And I think it saturates on the top at least. So basically you can, if you look at this outer one here, it basically just takes the end and start parameters and fades them from 1 down to 0. That's basically how that part works. And then limit base. Okay, so this is probably if it cuts off the bottom or not, which I'm guessing we use that for this one that comes down here. And then the other sections won't use that. So this triangle here is always drawn using those pyramid sections. I think there's 5 of them. And this is very basic stuff. We just draw the outer region and we draw the inner stuff. It's just this 2 quads. But yeah, so we always draw these 5 sections. And then depending on the section move parameter from the tracker, we move them on some sinus patterns or we don't move them. And then it will form just this whole pyramid here. This is one of the scenes where you actually, if you look really closely, this is where you can actually find the artifacts from video compression, because the video compressor is not completely lossless. It is a lossy compressor, but it ends up doing a really good job at finding tiles that match. So it's basically a big tile cache. We can get to that a little later. But it does a really good job at finding matches for existing tiles as it's trying to add new ones from new frames. So you basically can't find like any artifacts, but there's very subtle ones in either where 2 colors are really close together or motion is very slow. And if you look at the edges of the triangle, of course you won't see it here because this is not the video version, but you'll see the jagged edges here actually get a little bit stronger in the actual in the Super Nintendo version, like the compressed version. And that's because when it's doing tile matches for the slopes here, it finds a couple that are pretty similar, even though they were changing very subtly as this thing sort of scales up. I think the only other place you can actually find the artifacts is up in the globules effect. There's a couple times where some of the tiles for like the edges of these globules will align, and so you'll get like a globule of this color, but it'll have like 1 green pixel in it. And like you totally can't see it when it's under motion, but there are those very tiny artifacts in there. But yeah, so what we do is we just move this large section down here, and that's all synced with the music. So we have the kick that's making it sort of shake as it does in the rest of the demo. And then we have these pads that just do these. There's a major chord and a minor chord. It's very simple. And whenever those play, we accent that with the motion of this larger segment. And then, so that was sort of the first time through those bars of the music. And then on the next one, we start splitting it up. And all we're doing here is just moving those segments further away from each other. So their start and end values are the same. We just literally translate the different segments. And then here we start moving those on sinus waves as well. It's just moving them up and down. And I think we actually adjust. I don't think we move the position when we do that part. I think is it here? I think it's this evi thing. Yeah, time section move. So here we start moving the start and end of the pyramid things up and down with a sinus pattern. And it gets this kind of slidey motion look to it because the segments represent sort of different segments along the pyramid slope. I think it looks pretty cool. And then we also just adjust the camera movement as well. We just start panning around it. And I really like doing these kind of things that are really flowy and just kind of like you add little elements and things progress. One of the reasons I really like doing music as well is to kind of build structures like that. This was another place where I really had to control the camera angles or else the video compressor would just shit itself. And at that point, I think we basically, I ran out of time to make additional effects because as I was developing this, most of this stuff was developed in that last week at the gathering. And it was really fun, really cool, like creative area to work in. So I really enjoyed it, but it was very, very busy. and I would go back and forth between working on some of the effects and then working on the video compression. So like for half the week, we had this really dithery look that I really wasn't convinced about. And we just kind of, kept going back and forth. And it wasn't even until like, I think the night before the deadline that we had the video even fitting in the whole size and not taking ages to generate. Because that's the other thing is with the video compression based technique like this, you have rendering time, and if you're not careful, like I wasn't here, that can actually take quite a while. In fact, I think the compressor was even slightly slower than real time on the laptop that I used when I made this, and there were times when it was a lot worse than that as well. And the video compressor itself was actually quite complex to write, except when I realized that because it was bytecode based, I could do a people optimizer, and that kind of solve that problem. But the people optimizer, it ends up being particularly slow. It ends up being faster in F#, and I can explain why in a sec. But anyway, ran out of time to do additional effects, so I just did kind of this recap thing. And so then we kind of just revisit all the other scenes. Just kind of going through that same progression backwards for this one. Then it ends, and I think the program actually looped that time. Crashed on me earlier. Anyway, so that's basically it. And the whole like workflow for doing these visuals was test some stuff, see if I liked how it looked, go and change the C# code, rebuild this one little project, and then Rocket stays where it was. It's like if I go and change some of this code, like the rings thing. If I go in here and add another ring, for example, that I can just rebuild this, and we're running again. And when I don't have to move the windows around as much for the stream, then it's pretty nice. And I'm pretty sure this one actually, we did have more rings, and I had to cut that down again because of the video compression, because you get a lot of motion out here on these larger ones. So, but yeah, so that was a pretty decent workflow. And the only time when that really was not good at all was, of course, when the compressor didn't like something because something moved too much, and then we would kind of have to fix that by changing the motion somehow, and the iteration times on that are pretty bad. Can you change the color of the inner sphere in the one liney helical effect? Do you mean the globules one here? I guess you want to change this inner sphere? I can do that. Assuming that's what you meant, I'll go ahead and do that. That would have been here. Yeah, it just helps to visualize it. Yeah, no problem. I think it's here. No, these are the little ones. This is the big one. I can make it red. So that was one of the things too, is that if I make this red, it actually won't work now if we try to compress it, because there'll be too many colors on the screen. Actually, this frame might be okay, because we don't have any of the pink, but it has to be 4 colors. So I can kind of show you this under motion as well. Just kind of show you what that looks like. You can see this kind of gives those globules this shape here because it intersects the sphere. So it's really simple stuff. That's part of the fun. So when that's basically done, then we go ahead and run a different project. So this is Mammoth Machine content. This was before the Mammoth Machine, which is the tooling that we're using to do this, and the demo itself was very well separated. So yeah, so in this case, I work in this project, and then I go over here and I run this other project, which is, so that was Mammoth Machine content. This is Mammoth Machine. And what this will do is this will go and compress everything. Now the cool part is I left these changes in here. So we're probably going to see some video compression artifacts when this plays. But what this does, what this is printed here, is that there's different like modules, like assembler modules. So there's like a header, there's an entry point, there's init code, there's interrupt stuff. Let's see if, okay, there it goes. It actually crashed. Palette contains too many colors. So I'm going to change the color of this sphere back, and then we can watch this again. That was the video compressor that was saying, nope, can't do that. But it'll be a trooper through all this motion. It just won't work on playback. I can kind of explain why. Basically, the way that the decompressor works is it's the same bytecode based stuff that we still use in Memory Machine. But the thing is that so there's like opcodes for like moving a chunk of data into the palette memory or moving a chunk of data into video memory, which could be tile data or it could be map data. It doesn't really matter to the bytecode. But the thing is that you can only do DMA transfers within the v-blank period of the frame, which is not most of the frame. So you're very limited on the amount of time that you have to do that. And what can happen is if 2 frames in this system change too much, then the encoder will end up putting too many, like basically queue up too much data for the SNES to actually handle that frame, and it doesn't do a very good job at detecting that. It does the best job possible to try and get that down, but it doesn't have any idea about what the actual limit is. It just tries to do its best, and then I just sit there tweaking it until it works. But if you go over that limit, what happens is like nothing crashes on the SNES. It's just that you'll get locked out before the DMA actually finishes. So the DMA unit, I believe, still just keeps running, but then it can't finish its transfers because all the writes are being blocked. So this, by the way, this is what it looks like. And what was happening is there were DMA transfers that just couldn't finish in time. And so you have leftover map data here that points to tiles that are being overwritten later by the effect. So that's kind of what that looks like. And these will stick around until something overwrites the data on the map there. And so like the last few hours before the deadline, this is the kind of stuff that I was trying to get rid of. Because we always had this stuff. Especially with this scene, actually. Just because of the motion here. Let's see if it... I don't think it'll happen anywhere else, because I think everything else is still the same as the original demo. But what's funny about it, too, is that like if you have a corrupted video or something that you play on your computer... like in VLC or something, you'll get very similar artifacts for basically the same reasons. Just that it's doing delta coding, assuming that the previous frame is what it thought it was. And as soon as that previous frame wasn't what it thought it was, then when it applies to delta, it just ends up with something else wrong. Yeah, here it'll break pretty hard. That's funny. But yeah, so here's a couple of metrics based on the video compression itself. So the video compression takes like it basically renders all the frames of the OpenGL demo just with the same OpenGL renderer that we use in the preview thing. That's actually why we have the window open while it's doing that, is because we need to render all the frames in OpenGL. I actually don't think we have to push that to output or anything, but anyway, it's hooked up that way. And basically what it's going to do is it's going to diff all the different frames, and based on that diff, like the actual pixel data, it runs it through this like tile caching algorithm that we'll go over a little bit in a sec. And then it just generates this big old list of instructions. And so what you see here, this is the amount of instructions that it pushes out from that encoding step. After that, it runs a people optimizer on those instructions to do things like, okay, so you updated this part of the map, and then you updated this part of the map. They don't exactly overlap, but they're pretty close. And so to reduce the amount of times that we invoke the DMA, we end up combining those into one long run that will just output the data between them again. So it has a little bit of extra data, but it ends up working out better than doing the DMA twice, with the non-overlapping data. And so that's what this people optimizer is trying to do. And that simplified a lot of things because detecting those cases in the encoder, like while doing all the other things that the encoder has to care about, is actually kind of difficult. But then doing that as a secondary pass makes that very, very easy to detect, because we can do the people optimizer completely agnostic of whatever is generating these instructions, as long as it actually has knowledge of what should be on the map in those situations. So out of that, we have the total amount of instructions. So there's 72,379 instructions that these are like bytecode instructions that the demo runs before it's done. And then the total size of all that ends up being about 3.5 megs, which is below our 4 meg limit, which is basically the maximum size for a stock ROM on SNES. I think I don't remember if the memory mapping allows for more. I know that there were carts that were bigger, but I think that was done through bank switching. But the main reason why we wanted to target that is because a lot of the like flash cartridges that you'll get have that as a hard limit. So we wanted to stick with that. Yeah, and then the total time. This is the time it takes producing the video. So this is a minute and a half to produce the like 2-minute video, which is not great. I think if I recall correctly, on the laptop that I was using at the time, this took around 3 minutes to do the whole thing every iteration. So pretty bad when we actually had to change the content to please the compressor, but it's also not the worst thing in the world. The people optimization is actually one of the slower parts. That's kind of funny why. Anyway, so that's pretty cool. All of this is done in C#. So I kind of want to go over what's left. So there's something in here called Scribbles. And Scribbles is kind of the start of the tech that the current Mammon Machine thing is. So again, Mammon Machine is the tech that we're using to make these demos now that still does this kind of state diffing, but it does it on the level of some kind of better semantic of how the hardware it should be set up rather than actual image frames, which makes the data a lot smaller and also a lot easier to work with when you're doing more complex things. And that's of course the reason why Smash It was a quarter of the size of this one, even though it had much more advanced visuals. And again, that's a whole system about like trying to manage VRAM and the state of the hardware in addition to the CPU-based effects that we want to do eventually. And Scribbles was, I don't remember where the name came from, probably Scribbles on the paper as I was coming up with this stuff. But this is sort of the beginning of that. So we have a couple things as well. We have different kinds of tracks. And what I was thinking of for tracks is I wanted to have something like Rocket, where you could have tracks that describe, like here's a track that describes this section of video or this like the data for this effect or something like that. I think that I wanted the tracks, like I could control how much things were loaded in different tracks, basically just really kind of applying that Rocket way of thinking about things to loading data on the SNES. But of course, the only track thing that I ended up having was the video stuff. And yeah, which was, I think I don't remember. I'm kind of punting around in here because it's been a while since I looked at this code, because this is the older version of the stuff that I also haven't looked at in a while. Would have been about 4 years ago now, actually. Anyway, this is the instruction here. We have opcodes and length. Instruction here. We have one for loading palette data. And you can serialize that into bytes. We have one for loading VRAM data. We have one for just storing a byte and an address, and this is used to change video registers. So one of the things that this Scribble thing had is, in addition to having like those sort of tracks, which didn't really come up with anything, that's why I'm kind of hand-waving away that concept, is because it wasn't that well thought out, and it's kind of a bad name. But this also actually had a very small scripting system, and I believe we still use that here. Yeah, so this is the module that will basically output code to invoke the animation player every frame. So this is actually generating the assembler that goes in the demo. And what you have here is a little script here, Video motherfuckers. This is funny. This basically sets this video mode, enabled BG, whatever. This is basically like I'm trying to sort of encode what those instructions are going to be, but sort of upfront. And then I also I can fade values. This is, again, was this kind of notation for what the tracks might be like. This is actually parsed and also adds to the instruction stream in addition to the video. So like the video track is playing alongside this track that all this represents, and all of that gets combined together. So it's kind of funny. But yeah, a lot of that stuff just was kind of never that well thought out. But you have some cool stuff here. Movie00 was never a big fan of Windows uppercase variable names. I don't really have much of an opinion on that anymore. I just like that if you're working in a language, for example, that you have some kind of consistency. It's like if we're doing C#, we're gonna name our variables like this. C++, I'm a little conflicted about which one I should use at different times. But yeah. Anyway. So yeah, this is actually used to, I think, just fade in the screen and fade it out, basically. That's what these are. So yeah, so like this is an example of a register track, I guess was what that was. So like we can control this fade register. We have an initial value, I believe, or maybe that's default value, I'm not really sure. And then at 0 seconds, it's going to have this value. At 0.3 seconds, it's going to have this value. 120.2, it's going to have this value. And then 120.5 is going to have this value. And that will fade the screen in and out as the video plays. So it's kind of separate from that. And then this was the video track, which could play this video from this time to this time. And then I think these were some things about some settings about the banks. Can't exactly remember. So this is like the script of the demo. And then there's also a video compressor in there. That's kind of fun. Yeah, and then so we have to give that also something that'll give us the video here to actually have it serialize everything. But yeah, gonna hand wave a lot of this because it's not that crazy. The heart of this ends up being this animation serializer and an iVideo generator interface. So a video generator has a name, and I think it only has a name to be able to like print debug stuff. Oh yeah, no, actually no, it has a name to be referenced by the script. That's what that is. So here, I think the anim test video, I think that's actually how it matches that. So we're gonna have a video identified by this that's playing here. I think, let me go to this. Yeah, that's what that is. And this particular video generator is going to, it has a renderer, which renders the OpenGL demo, and it has a sync player, which plays back the stuff from the Rocket data. And then given a time, it's going to generate a frame into this frame buffer object. So it's going to update the sync, it's going to render the frame. We then grab the screenshot from the renderer, and then we set all the pixels in this frame buffer, and away we go. So we generate frames into this frame buffer based on this time. Now, once you have that kind of interface that's going to give you some video, then you can build the compressor. I don't know why this has multiple. Again, the design here is never that well thought out, but eventually we have the serialize function here, which given an animation, yeah, that's another type here. I think this is just like an entry in the script system. Yeah, this will basically, this is actually the thing that takes a bunch of tracks to put them together. That's actually not what I'm looking for. Sorry, I'm a little scatterbrained here. It's been a long time since I looked at this code. But I guess it's kind of fun just to see all the different pieces. The video track should actually be the part we're most interested in here. In particular, the video track serializer here. I think this is the most interesting thing. I think this is what we're after here. Yeah. So this is the thing that is a track serializer, and this will serialize a video track into bytecode. And I believe this is the main part of this interface, is serialize the next frame. So given a frame time, it's going to serialize, it's going to give you an enumerable of instructions for the next frame. And so this goes over the segments, which don't really have to worry about that because there's only one segment in this case. And then just renders the correct, it gets the video generator for that segment and then renders the correct frame of that and then generates, goes through the video compressor to serialize the next frame from the frame buffer and then returns all the instructions that would have given it. So I guess this is a little more glue as well. But the point is that then we have a video compressor, which is going to be way down here. And I guess this is kind of the heart of what we're doing here. So we have, this also has a track thing. That's kind of funny. We basically have the serialized next frame thing. I think that's the most important part. So every time, this is just a mutable object, this compressor, and you feed it a frame and it will give you an iterator over instructions. That's basically all this is. Now, the first thing this does is it's going to skip every frame. So it only generates instructions every other frame. This is just to cut the frame rate in half. If we don't do this, it'll be way too big for this SNES. I'm actually kind of curious. Actually, that'll be too slow to just test, but I mean, it's not going to be, I don't think it'll be twice as big as the original video because I think there'll be less motion. So I don't think it'll be twice as big, but it'll be too big. So I can't do that. But then what it's going to do is it goes through, I guess it has multiple palette encoders. Oh no, it's going to take the palette encoder. So there's, I guess I split this up into a couple different things. I probably have one that encodes, I probably have a couple of like sub encoders. One of them is going to encode changes in the palettes as the new frames come in. So I think that's what this is. Serialize next frame for the palettes and then return all those instructions. And then we start doing like the tile cache stuff. Now, I'm probably going to be a bit scatterbrained talking about this as well, because it's been a long time since I looked at this. But basically, if I remember correctly, the idea is that we have this big cache of tiles. And I think, let's see if I thought I had an object called tile cache. Maybe I don't. I think the tiles are just on the video encoder here. So basically, we have these two pieces of data here. We have this array of tiles that represents basically a whole map of different tiles that we keep track of. I believe there's space for 1024 tiles. That might be arbitrary, though. I may have just made that up for this particular purpose. And then we have this parallel array, which is just a bunch of indexes into these tiles, and that's going to be our map. So the map data covers the whole screen. So it's a 256 by 224 screen, but each tile, I believe I did 8 by 8 tiles for this. I don't think I did 16 by 16. I'm pretty sure I did 8 by 8. And because I think the SNES you can actually choose depending on your background mode, but I'm pretty sure I used 8 by 8 tiles, and this is a 4-color mode. So the tile represents that. I think it has a little bit of metadata to figure out if it's like live or not, because so for the tiles, we always keep track of 1024 tiles. And then we always keep track of a large enough map for the entire screen. And okay, in this case, it actually looks like we regenerate a map. Wonder why that was. So yeah, so for a tile, we have, planes is 2, so it's a 4-color tile. This is the actual data for the tile. We have whether or not it's used, and we have a dead frame counter. So if it's not used, we have this dead frame counter. We're going to invalidate a bunch of tiles. But I believe if we ignore the palette stuff, because it's not that terribly interesting, we should be able to sort of work out how this algorithm worked. So here it looks like I invalidate all the tiles from the last frame. So what I'm probably doing is just taking all the tiles that, basically all the tiles, and if they're used, they're not used anymore, but then we reset their dead frame counter, or if they already weren't used, we're going to increase their dead frame counter. And after 200 frames of a tile not being used, we're just going to drop that tile from our tile cache. So that's sort of the heart of this algorithm, is that we have these tiles that are these 1024 positions for a tile cache. And we keep track of ones that we know we've actually used. Yeah. And then what we're going to do is for the incoming frame, we're going to basically generate a whole new set of tiles. And then it looks like we fill the map. And so we probably, what happens here is it probably generates a whole new set of tiles and a whole new map for every incoming frame. So the incoming frame is just pixels. So it's not like encoded the way the SNES would actually render it. It's just pixel data. So we have to actually build the map for that, and we have to build the tile set. So I'm fairly certain what happens here is this has nothing to do with our cache tiles. I think this just goes in and just converts the pixel data into a SNES friendly format. So we have a list of tiles and we have the map for that screen. Then I think what we do is, it says update the tile table. So what I think this does is this will end up updating the, so it takes all the new tiles for the current frame that it just processed, and it's going to add those into our tile cache. But it's going to skip ones that are sufficiently close to existing tiles that are already in the cache. So it looks like what we do here is we take all the new tiles, and we're going to try to find a best match for that, given the tiles that are already in our cache. So here we go through our tiles in our tile cache, look for the old tiles, and then we basically try to match our new tile with the old one and the current palette. Now this 300 here is some kind of error tolerance. Now I think my error metric is actually pretty naive. I think I just take of the 8x8 pixels in the tile, that each one of those has 0, 1, 2, or 3 as their value. And I think what I do is I just take all of the every pixel from the old tile and the new tile, and I just add their difference to a big number. And this is some threshold that basically determines a match. So if this is a lower number, then it's going to be a lot stricter for what it takes to be a match. If this is higher, it's not going to be as strict at all. So I bet if we turn this up to 3,000, we could get some really funny stuff. I'm going to let this run in the background while we talk about this, because I want to see if this does some funny stuff. It should also encode a bit faster as well. And it's always a balance too, because the lower numbers for this will obviously give you a higher quality image, but it may be too slow to actually play back on the SNES. Higher ones may give you a crappier image, but then it'll play really fast, but it might not actually, because it might also blow your tile cache a lot faster. So it may not actually be that much better anyway. So there's some encoding details that make that not always so clear cut. And that's one of the things that was pretty interesting about this, but I guess that will kind of become clear as we talk about this more. So yeah, so you basically try to find, given all the tiles that are in our existing tile cache, we try to find the best match. This is a really naive algorithm, you'll notice, but I kind of did it that way on purpose because we did this really quickly. So just doing it kind of the dumb way was kind of the only way rather than trying to be too clever, where I feel like if I did that, I probably wouldn't have been able to write this at all. I like that kind of make it fast and then make it fast mentality, if you know what I mean. So you just kind of do it the way you know you can, and then you can optimize after it works. So I think all this is just trying to find, a best match. So if it did find a match, something that could be considered a match. By the way, this checks for matches as the tile is, but the SNES hardware can also, in the map data, support flipping tiles horizontally, vertically, or both. So we check when we compare tiles. We check all those different orientations. And the reason why we do that is because if we may not have a match with one orientation, but if we flip the tile, it may match another tile that we already have. So that's kind of what we're trying to do. So this is building up sort of new map values depending on those things here. So these are different bit masks for the different flips here. So that's what that's doing. When it finds a better tile for that, I think what it does is, so for here, what does it do here? Yeah, so it's basically adding a bunch of new tile indices here and then updating the map data if it found a good match. So this is what happens if you have that error tolerance really high. This is what it looks like. And I mean, it just looks like a crappy video. And so the reason why it looks this bad is because it's when it's introducing new tiles, it sees the old ones in the maps, and it just accepts ones with a really liberal definition of a match. So it looks quite a lot different. A lot of jagged edges. Our data, though, is a lot smaller in this case. Here, this is about 1.8 megs rather than the 3.5 that we had. And here you'll notice it actually took longer to encode. Now that could be for a number of reasons. My guess is actually that it ended up doing more tile compares because it couldn't early out if the error was, like I think normally if it finds a really good match, then it can early out of all the subsequent checks as soon as their error metric is larger than the best one that we have. Where in this case, I don't think it can do that as often because so many tiles are potential matches that I think it's able to compare more per new incoming tile. So I think it actually gets slower, which is interesting. Yeah, so that's what that is. So I think yeah, if it didn't match anything and we either had a better one than the last match or we don't have a best match yet, then we update our best match here. Not sure what this does. Speculate who's Chris? Chris is actually a pretty good friend of mine. I slag him off a lot in my code and stuff, but he's really a great guy. Oh, that's funny. I need to remove that stuff before I make these videos. But yeah, I'm just gonna hand wave this away for now. Don't feel like digging into all the details here. But basically, that's what it's doing, is it's going to update the tile cache if there's any new tiles that basically it didn't find matches for. And I don't think it will ever try and overwrite an existing tile. I can't remember if it tries to do that or not at any time. I think what it relies on is the fact that the tiles will expire if they haven't been used in a long time, and that will just sort of free up space in the cache. And I think it only relies on that. I think if you end up with a match, or like you can't find a match or something, I think it will end up just dumping the tile. Boy, funny comments are the only reason I watch, though. Jesus, Chris. Hey, he looks a bit like Jesus. Oh yeah, so here we go over some of the new tiles. Okay, no, here we actually do overwrite tiles. If the old tile is not null, but it's also not being used, we can overwrite those. And that makes sense because that's safe. I'm surprised it doesn't try to like sort them by usage though, but might have just been because that was expensive. Anyway, when it's done with that, and it's sort of figured out semantically what tiles it needs to update, then what it actually does is it goes through all the new tile indices and actually serializes instructions to update those specific tiles. Then what it does is it serializes the new map data. And I'm fairly certain all this does is it looks for chunks like runs in the map that differ from what the map was in the previous frame, and then outputs these load VRAM data opcodes to load a bunch of here it serializes a map range. And that ends up being basically it. There's some more details on how this works, but I think that's basically the whole compressor. So it's actually pretty simple. I actually quite like this little piece of code. And then, of course, the next part is that we have optimizers. And these optimizers operate on a list. So they just take the entire list of instructions and just will mutate that list. Now, the problem is this list is like a vector. So it's actually like its elements are contiguous in memory. I should have used like a linked list because we're going to do a lot of insertion and removal like in the middle of the list. And that's one of the reasons why this is so slow. It's just because I used the wrong container. But it works. So there's a load palette data optimizer, and this will basically try and find opcodes in succession. So we have like if the current opcode is load palette data and the next opcode is load palette data, and their addresses line up, then we can remove the two instructions and insert one that's basically the two of them put together. So we just concatenate those two instructions in place. The VRAM one is basically exactly the same. So I think that's all that does. And I think there was another thing here. This min map data block size. Yeah, so this min map data block size thing, this keeps it from generating map updates that are only like a tile or two. And it forces it to basically try very hard to merge that with upcoming changes. Because again, if you changed every other map tile and you had all those as separate DMA accesses, that would be way slower than just doing them all at once, even though you're transferring extra data. I need to actually do the numbers at some point to quantify that more, because I know from doing this in practice that was the case. Just experimentally, but it should be entirely deterministic how that thing works, and I want to at some point do this a little more rigorously and go over like what are the actual bounds for this, how many bytes can you transfer, what is the actual overhead for invoking the DMA, because if our new tech is still using this stuff, we need to kind of hammer down on those values, and then we should be able to, for example, at sort of compile time, figure out if we're gonna blow that limit. And either warn the user or do something about it. But in this case, I wasn't that rigorous, and I think I would need to do some hardware testing as well, because I don't know if it's as clear cut as just looking at the data rates. But yeah, ended up making it work anyway. Move away 000. I don't know. I'm always surprised at how much better contiguous arrays are. Even in a lot of cases, you'd think linked lists would be better. So in this particular case, I know linked lists would be better. And that's because when I ported this to F#, instead of using a contiguous array like this, I used a linked list to implement it. And the people optimizer was like 10 times faster or something. It was ridiculously faster. And that makes sense, because in this case, we're talking about an array of like, I don't remember what the numbers here were, but they were like 70,000 instructions or something. And if you're inserting and removing a ton in the middle of that list, that's a big enough constant that becomes significant. Whereas if you implement this with a linked list, in particular a linked list where if you're using a functional language, you're doing that kind of recursion on the tail of the list. And so you're kind of rebuilding the lists every time, and you just like look at the tail and then, oh yeah, we'll take that thing's tail and then pop new things in the front of it. It's extremely fast. So, I mean, when I say that, of course, I'm talking about this algorithm in particular and the way that we were doing this. But in that one particular case, it was a lot more appropriate to use that structure, which I should have just done in the first place, because I'm pretty sure .NET has linked lists. But anyway. But that's basically all I got, except for sitting here and tweaking some of these parameters just to kind of show you what happens when things go bad. Speculo, is the emulated DMA performance more or less the same as running on real hardware? Do you mean emulated in like HEGAN? Because then it's as far as I know, it's pretty accurate. But the thing is that when we're doing, like, I don't emulate any of that in any of my tooling. I just kind of try to reduce what we do every frame. So, yeah. Yeah, the emulators are supposed to be pretty accurate as far as that goes. I haven't seen really any discrepancies there. So I guess I could learn how that works in more detail from the emulator code, but it's also a pretty well documented piece of hardware. It should be entirely possible to figure out a compile time, like deterministically, are we over a limit or not. I just didn't do it for this one. It also gets a little more complicated when you're running like user code. But I guess scheduling wise, it can do some clever stuff there to always move the user code to the end of all the DMA runs, so that at least when it's finished, it can run into the area of the frame out of VBlank as well, as long as it's not going to actually touch as long as it's not going to actually do DMA. Because typically, like if you want to do a polyfill or something, you're going to do it double buffered, where the CPU is chugging on it during most of the frame, and then on the next VBlank, you're going to actually upload everything via DMA. Yeah. So there's this min tile block size. If I turn this down, and I want to also change this stuff back in the demo. I think that was the only change. If we do that, then I think we'll basically have the demo working as it would before. But it should... I don't think it'll play back correctly now. Because I'm pretty sure that sort of mixing like map updates that were close to each other but not quite touching, I'm pretty sure that was actually very significant in trying to make this work. You also notice the aspect is slightly different in the regular demo. Things that are a little bit taller here, and that's just because the Super Nintendo doesn't actually have a square pixel aspect ratio. Can't remember what the actual ratio ends up being, but it's a little bit wider on the actual SNES. In the Meme Machine tooling, we actually simulated that in our little preview window, but the scaling just looked so bad that I ended up just having it be per pixel on the PC, because I just thought it looked nicer, even though it was the wrong aspect. That's optimizing. Yeah, see there it already fails. The data rate, you'll notice, is actually a lot smaller, because it can, like, it's more optimized now because it only updates bits that it actually needed to update, but it pushes it over the edge because it has to invoke the DMA more times for very small updates in a lot of cases. So you can see it reduced our data rate, but it can't play it back fast enough. So that was sort of the other thing that we have to balance. Because one of the questions I get asked about this demo in particular is oh, if you had video, why didn't you do something more complex? And this is why. Because it still has to be played back on a SNES, and SNES is still very slow. So I think that's kind of interesting. It's probably possible to do a better encoder as well. One of the things that's kind of popular in the demo scene is there's this song called Bad Apple, which has this really cool black and white music video, and it's actually really popular to make video conversions of that on different platforms. And I think it'd be really fun to do a SNES one, just because I've done video compression here before now. I think it'd be fun to do a SNES version of that, which is pretty cool. Maybe I'll do that at some point, because I would like to actually explore this more, just because this was actually my first time ever writing a video codec for anything, really. Just kind of applying that concept, and it was extremely fun to do. Even on such a time budget, it was just really cool. Base effects, some of the glitches are cool, yeah. They're not cool when it's only one or two of them happening, but yeah, could have a cool look based on this. Speculo, yeah, I figured. But yeah, but that's all I got for you guys. Again, this is the last stream I'm going to be doing for the next few weeks, because I'm going to be doing some revision stuff. So I think it was what's today, the 2nd? Yeah, this is the last one. And then I think I'll be back on the 23rd. I'll be back. So in 3 weeks I'll be back, and then we'll go over the revision stuff. And then the weeks after that, if we don't end up spending more weeks on the revision stuff, then I think this will be fun to just make stuff every Sunday. Make some random stuff with the tools. Movie 008 beat Zelda yet? No, I'm putting off beating Ganon because there's so many side quests in the game, and I know that when you beat Ganon, the game ends, so you just kind of have to pick up from an older save point or something. I don't want to do that. So I've just been doing tons of side quests. I've got like 70 or 80 hours in that game now. It's really fun. Because I'm just playing it like, oh, I got 5 minutes here, 10 minutes there, and you can just pick it up and put it down, so you rack up so many hours in that game. Base Effect, I'll be watching your pod remotely from revision stream. Can't afford to travel. Gotcha. I think it'll be cool. Movie 008 just got the 4th beast. I kept getting distracted. That's totally how that game goes. I'm just gonna admit. Oh, a shrine. Oh, a little pinwheel up there. Oh, I bet a Korok is hiding there. Oh, you can build a house? Yeah. I really like the new Zelda. It's a silly game. It's just fun. Movie 008, did y'all break the Switch yet? We actually released we released our exploit kit. Which, yeah, there's some things about that. I think I linked this before. Still waiting to run Rust on mine. Yeah, I can't really talk about anything beyond the stuff that we've publicly released. And to be honest, I'm actually not keeping up with that group's activities as much right now, just because of the revision stuff. So if I told you something, it'd be wrong anyway, probably. But yeah, that's just an exploit kit for using a little exploit that'll give us basic memory read and write, and then some code execution via ROP, but not arbitrary code execution. But it's cool. Anyway, I think I'm going to head out now. Thanks, guys, for watching, and I will see you in 3 weeks.